morning, everyone. Good afternoon for the people who are in Asia, or good evening. Welcome to this second session of the third Poema workshop. It's my great pleasure to introduce today Lihong Zhi from the University of Chinese Academy of Sciences. Lihong is a top expert in symbolic computation, hybrid symbolic numeric algorithms, polynomial optimization, and today she will talk about her joint work with Shmuel Friedland and Jingtong Ge about infinite dimensional quantum Strassen theorem. So thank you, Lihong. We are glad to hear you today.
Thank you, Mark. So thank you very much for inviting me to give a talk in this workshop. So actually, I really enjoyed to participate this workshop. So today I will introduce my work, joint work with Shmuel Friedland and Jingtong Ge, my former student. So actually, this is not a topic that I'm familiar with. So I will go, I'm not sure, I guess maybe some of you also not familiar with this kind of the probability theory and also this quantum theory. So that's all new for me. So I'm just trying to learn about these things. So the probability distribution is defined the following. So a proper distribution of a countable set. A is a map. So mu is a map satisfied that you map each element in the A to a number, a real number in the interval of the 0 to 1, and satisfy that the sum of this probability equal to 1. Here the UA represents the probability of the A in the set A. And the support of a distribution is a set of elements with a positive probability. So all these notations and definition actually comes from the Justin Shi's PhD thesis. And what is the probabilistic coupling? So we let this as distribute A denote the set of the all proper distributions over A, and the probabilistic projections defined here. The pi1 is pi1 mu defined at A1 is equal to the sum up this probability over the elements in A2. And pi2 actually is the sum of all the probabilities over the elements in the A1. So if you think about a finite case, so this is very similar to you have the probability distribution as a matrix. Then you sum up the rows or the columns of the matrix, you get this kind of the marginals. So the pi1, pi2 are called the first and second marginals. And the coupling is defined here. So if we are given the mu1, mu2 are distributions over the A1 and A2. And the joint distribution over this product or A1 times A2 is a coupling of the mu1, mu2 if it is satisfied this first marginal is mu1 and the second marginal of the mu is equal to mu2. For example, given any two distribution, subdistribution u1, u2 of the A1 and A2, we always can have the coupling. It's an independent or called the trivial coupling. Is defined below. So you just times the mu1 A1 to the mu2 A2. So then the marginal, the first marginal actually if you sum up this one is equal to 1. So defined at A1 is equal to the mu1 A1. So the projection satisfies this condition. Similarly, we have these two. So it's a trivial coupling. And so it is more interesting if you impose some conditions. For example, if you impose some condition equal, then you have this identity coupling. So let mu be the distribution over a set. Then the identity coupling of the mu is defined below. So it only has the non-zero probability at the if A1 equal to the A2. Otherwise, it is zero. So if you sampling from this coupling, it will yield a pair of equal values. And what is the probabilistic lifting? So if you have the mu1, mu2 bit distributions over the A1 and A2, and R is just a binary relation, and a distribution mu over the A1 times A2 is a witness for the R lifting of the mu1, mu2 if it satisfies the following condition. First, of course, it is a coupling of the U1 and the mu1 and mu2. Second, its support is included in this relation, binary relation set. So when a witness exists, then we can say that mu1 and mu2 are related by the lifting of the R and return this form. So the R actually is just a logic. A1 some relation means that A1 and A2 satisfy some conditions. Phi is a logical formula. For example, for this identity coupling, we impose the condition that the A1 equal to the A2. So this witness the lifting mu equal to mu. And actually, two distributions are equal if and only if there is a lifting with the constraints is equal. And there is a very well-known theory about the sufficient necessary and sufficient condition they exist a lifting. So it's given by the Strassen in 1965. So assume that mu1, mu2 are two distributions over A1 and A2, and R is a relation. Then there exists a lifting if and only if for each subset S1 included in the A1, the mu1 S1 is less than or equal to the mu2 RS1. So RS1 actually is just the image of the S1 under this relation. So means that include all the set in A2 such that they exist A1 in S1 such that A1 and A2 has some relation, satisfy some relation. So here the probability is just means the sum of all the probability of the A in the S. So this probabilistic coupling are closely related to some cryptographic security for checking, for the formal proof of the cryptographic security. So, and also it has been applied to the differential privacy. So differential privacy is a quantitative rational property modeling statistic privacy. So it is quite now there are quite a lot of people are studying this kind of the differential privacy. So it is related to this kind of the probabilistic coupling and lifting. So, but it is a kind of they extend it to the approximate case. And this Strassen theory actually you can when these A1 and A2 are finite set, actually it is also related to, can be proved by this kind of minimal cut and maximum flow theory. So it is a quite well-known theory. So then So how we can extend this kind of theory to the quantum computation. So here I introduced some basic notations of the quantum theory. So actually this has also been introduced by the Sabine in her first talk. So she also introduced some notations. So here we just review some that I will use later. So here the H is a separable cubed space over a complex field C with the inner product defined by the Y conjugate transpose times AX. So if you have if H is a finite dimensional and you have a basis, then H can be identified with the complex field, the vector field Cn. And the BHP is the set of the bounded linear operator from the H to the H. And if H is finite dimensional, this L actually is equivalent to the matrix, n by n matrix. Then the adjoint operator LV satisfies this, the inner product of the LXY equal to the XLVY. Then we come to the trace. So the trace is an important concept in the quantum computing. So the trace of UL, the operator is defined to be the sum of the LEI, EI. EI is an orthonormal basis of H. Actually, this trace is independent of the basis, ER, the choice of the basis. If you look at this L as a matrix, the trace is just the sum of the diagonal elements of the matrix. And then we have this density operator. The density operator actually is the set of the positive semidefinite operator. So it is self-adjoint and satisfy for each x in H. Lxx, the inner product is large or equal to 0, and the trace of L equal to 1. If you think about the finite dimensional case, this just means this operator is just a Hermitian matrix, positive semidefinite. And then in quantum, you think of you are dealing with this. Hello?
There is a question on the chat from Monique, who is asking the following question: does the trace of L always exist?
Yes.
And
yes,
is it finite?
Exists. Yes. So we have proved that it also exists for the infinite dimensional case. Okay. Separable. Okay.
And it looks like there is a question from Giorgio also. Giorgio, if you want to ask for it or if you want to write it in the chat.
Thanks. No, it was just a small remark to understand if I am on the same page, but it was in previous slide when you defined the relation between the two distribution. So it is necessarily not symmetric. So it can be that μ1 is in relation with μ2 and not the converse.
Here.
Yes. So this relation is not symmetric.
Yes, not symmetric.
It's not symmetric. So there are a meaningful example when this happens. Okay, thanks.
I don't, most, it is not symmetric, but maybe there are some examples will show that. Okay. So now we have this tensor product of two separable Hilbert space with the induced inner product here. So this inner product is defined by the inner product of the xu and y times yv. And then we have this partial trace. So the partial trace actually, so if you we will see later actually, but if you define for the rank 1 density operator, then it can be generalized to the any rank. So for the rank 1 density operator, the partial trace is quite simple. So you define as the partial trace of the law with respect to the first space A1, you trace out this XU vector, XUV, and times YV. So here the UV I will introduce later. This UV, actually you can think about this UV is just, it's a linear function. So you can think about it, this is just a transpose, conjugate transpose of the vector U. So it is well defined, even for the infinite dimensional case. So the partial trace can also be defined. So what is the relationship between this probability and the quantum theory? So we can see that from the probability theory, we have this probabilistic distribution. In the quantum, we have these density operators. And the weight of the distribution corresponding to the trace of operators in quantum theory. And this Cartesian product of the two space corresponding to the tensor product of two space. And these marginal distributions is equivalent to is corresponding to the partial traces. So with this correspondence, you can define this quantum coupling. So assume Rho 1 is a density operator in H1. So it is positive semidefinite with the trace 1. And Rho 2 is a density operator in H2. And then here the Rho is a density operator of the tensor product of the H1 and H2. Is a quantum coupling for the Rho 1 and Rho 2 if it is satisfied this condition. So the partial trace 1 Rho equal to Rho 2. So it trace 1 maps Rho to the H2. And the trace 2 Rho maps to the H1. So it's a Rho 1. So here the SH means the self-adjoint operators, and S plus means S plus H is a set of the positive semidefinite operators. And here plus 1 means the trace equal to the 1. So it is the density operators. Then we have this kind of quantum lifting. So we have the Rho 1 and Rho 2 density operators of H1 and H2. And we define some X. X is a closed subspace of this tensor product of the H1 and H2. Then this Rho is a density operator in the H1 tensor H2 is a witness of the lifting if first Rho, of course, it is the quantum coupling for the Rho 1 and Rho 2. It means the partial trace of the Rho equal to the Rho 1 and Rho 2. And the second condition is support of the Rho is a subset of the X. So here the support means the subspace spanned by the non-zero eigenvectors of the density operator. So then we have this quantum Strassen theory. So suppose we have the H1 is a tensor product of the H1 and H2, and both space H1 and H2 is of the dimension is finite dimensional, and the Rho 1 and Rho 2 are density operators in H1 and H2, and X is a closed subspace of H. Then the following are equivalent. So the Rho 1 is a coupling with the Rho 2 with respect to the X. If and only if for all Y1 is a density operator in H1 and a Y2 in the H2 satisfy this condition. If they satisfy this condition, then we have this relation, the trace of the Rho 1 Y1 less than or equal to the trace Rho 2 Y2. At the first glance, you may think this is quite strange. So with this condition. However, it looks very similar to the Strassen theory. So the mu1 mu1 and mu2 has a witness set if and only if this condition satisfied. So these two are very similar looks. So also this kind also we have the application. So it has also been applied to the rational proofs for the quantum programs. So with a little modification, I will show that this is just modify this Zhou and Yin and Yin's paper. This definition relax it in their definition. It is equal. Here we extend to the generalized to the less or equal to the low one, the partial trace of X. Partial trace with respect to the second space is less than or equal to the low one, and trace 1x less than low 2. So for this quantum Strassen theory finite dimensional case, actually it is they exist a lifting if and only if the mu low 1, low 2 x equal to 1. Actually, this is the optimization problem. And it is maxima if and only for this maximum of the trace x, px. Px means the projection projected to the x space. And x satisfied, x is positive semidefinite, and the trace satisfied, partial trace satisfied this condition. You can see this is just a semidefinite program problem. So why we can kind of these two are equivalent? So this is just a sketch of the proof. So if they exist a row with a satisfy, this is the density operator, and the support satisfy this condition, and the partial trace satisfy this condition. Then we have that this row, the trace of the row px equal to the trace row, because the row is the support is included x. So this trace row, we know that the trace row is equal to 1, which means that the maximum value of this mu should be greater or equal to 1. And on the other hand, for any feasible solution, it will satisfy this condition. The trace of x px, of course, it is less than the trace of x, and this will be less than the trace of the low 1. So this is equal to 1. That means that the maximum value, so it only can be equal to 1. So this direction is easy. And for the second direction, if the mu, the optimal value is equal to 1, then we have the maximum is reached at this x max. And we also can prove that from here you can show that the support of the x max is a subset of the x. And also the partial trace will satisfy this condition. So it means that if this maximum value equal to 1, then we will have this lifting, low 1 lifted to the low 2. So then it is a semi-definite program. So you can write down the prime problem and the dual problem. And here the A is the projection, and B is the diagonal matrix, block diagonal matrix defined by the low 1 and low 2. Phi X is also a diagonal matrix defined by the partial trace. And the phi star also defined by this is just some condition appeared in the and in Zhou and Yin's paper. And we will check for this semidefinite program, the strong duality actually holds, because we have find a primal feasible set, feasible point X. So X actually just the tensor product of the low 1 times tensor low 2. So it is a density operator. and also satisfy this partial trace, this condition. And also we can find a dual strict feasible set, feasible point here. So we defined this Y. You can check this Y will satisfy this strictly. So then we have that we can solve this. So we can solve this Semidefinite Program problem by any well-known software. So the finite dimensional case. So actually the problem has been solved. So now we can look at for the infinite dimensional case. So the people are it is very intuitively that we will think about the projection. So you project this kind of infinite dimensional case to the finite dimensional case. So we introduce this orthogonal projection operator Pni. So we are given the H. It is a tensor product of H1, H2 with the basis Eni. So this can be infinity number of the Eni. And the projection means that it projects on the Hi on the subspace spanned by the E1i to the Eni. And our first theory is about, so if suppose H is a tensor product of the H1, H2, and these two spaces are infinite dimensional separable cubed space, then in the first case, when this X is a closed subspace, if X is a finite dimensional closed subspace, then it is simple. We can just use this orthogonal projection. We can just generalize the finite dimensional case. So rho 1 and rho 2 exist a witness, the witness of the quantum lifting, if and only if this optimum value goes to the 1. So the mu n is defined by the truncation. So projection. So you project it to the finite dimensional case, and this can be solved by any SDP tools. So then you check if the limit equal to the 1, then there exists a lifting. So when the X is finite dimensional case, then it is simple. And the difficult case is that when the H1, H2 be infinite dimensional and X is also infinite dimensional, then we cannot solve the previous one. We have to introduce a new optimization problem. So this is the minimum, the partial trace X partial trace with respect to the second space minus rho 1, the one norm plus this one norm, the minimum. If this minimum goes to 0, then we have this if and only if. So sufficient and necessary condition. So actually, this kind of infinite dimensional Hilbert space actually are required in quantum program theory when a data type is infinite. So it is necessary that to consider to generalize that this quantum strength theory to the infinite dimensional case. If you look at this here, actually just means that the partial trace has to convert to the rho 1 in the norm 1. So in order to study this kind of when the X is also, the subspace is also infinite dimensional, we have to introduce some notation. So first, let KH be the set of the compact operators, and YV is a bounded linear functional defined here. And L is a compact operator if and only if L has a single value decomposition. So here, so the finite dimensional case, it is simple. It is a matrix. We know that we have this kind of the SVD decomposition. So for the infinite dimensional case, if it is compact, we also have this kind of SVD decomposition. And the sigma I is arranged in the decreased order. And the limit of this sigma I will go to 0. Here, the GI, Fi also are two sets of orthonormal sets of vectors in H space. And we define those, we can define the norm, P norm. So we can see the L infinity norm is just the theta 1 L, and the L1 norm is the sum of the theta I L, the singular values. So here,
Lihong, there is a question from Victor Magron, which is the following: why don't you consider, for instance, von Neumann algebras of type 2, 1 to ensure that the trace is well defined?
So I think so this, yeah, it is interesting. So I think maybe. So I'm not an expert in this function analysis. So maybe it's possible, but we start with the this separable Hilbert space. So I guess it is possible. So we proved that all these trace and partial trace exist.
Okay, thank you.
Okay. Then we defined this kind of the trace class operator. So what we are trying to start is this trace class operator. So trace class operator is a set of the operators satisfying the L1 norm is bounded. So in this case, so assume that H is a separable Hilbert space with this basis EI. Then for rho is here with this SVD decomposition in the trace class operators space. And then we have this trace rho is also bounded. So trace rho actually is less than or equal to the 1 norm. We know that if rho is a positive semidefinite, then it is just equal. So interesting is that when the H is the tensor product of the H1 and H2, the norm one of the partial trace of the rho is also bounded. And we can, for the partial trace 2 rho is also bounded. So if rho is belong to the set of the trace class operators, then its partial trace also belong to the trace class operator, means that the 1 norm is bounded. Then here we will have the 2 convergence. We have to define 2 convergence. One is the weak convergence, another the weak operate convergence. First, let's see the weak convergence. What is a weak convergence? Assume that H is a Hilbert space, Xn. And Xn and X is belong to the H, and the Xn converge weakly to X if for any Y in the H, space H, the limit of this inner product converge to the XY, the inner product of XY. And for the weak operate convergence, so assume that H is a Hilbert space and AN is a bounded linear operate, then AN converge in the weak operate topology to A if we have for the any XY in this Hilbert space, the limit of this inner product is equal to the XY. So on this trace class operator space, the weak convergence does not equivalent to the weak operate convergence. So they are different. So let's look at this example. This simple example. We consider this En, Env. En are the you can think about the En as a vector with only the one at the position n. And En, Env belong to the BH. Then this operator converged in weak operator topology to 0. However, it does not weakly convert to 0, because if you use this identical operator, then the inner product actually goes to 1. So these two are not equivalent. So this will introduce some difficulty. So let's look at this one. So suppose rho is a trace class operator and it is positive semi-definite. Then of course we can see that the partial trace also a trace class operator and a positive semi-definite. We can prove it. And because rho is a positive semi-definite, its one norm is equal to its trace. So then you can just it is easy to see that this is equal to the one norm of its partial trace. And we have this weak operator convergence. So the trace, we suppose that this rho n is a trace class operator, which is positive semi-definite, and the rho n converges weakly in weak operator topology to rho. Then we will have that rho is also a trace class operator, positive semi-definite, and it's the limit of the infinity of this trace rho n larger than its trace of the rho, its limit. And we also have this partial trace, the limit of this partial trace. It is big or equal to. And only in the case that the dimension of the HR is finite dimensional, then we will have that we will have this weak operate the partial trace will converge in the weak operator topology to the partial trace of the rho. So here is another counterexample. Suppose that when the H1 is infinity, we consider this rho. We consider this density operator rho n, and then we can see that we can show that this En tensor E1 will converge weakly to 0, and that means that the rho n converge weakly in weak operator topology converge to rho equal to 0. However, so since this H2 is finite dimensional, then we have this trace, the partial trace also converged in weak operator topology to 0. But for the H1 space, it is infinity. Then we will find that the partial trace 1 rho n, will not converge to trace 1 rho in weak operator topology. So that's difficult. That will cause some trouble.
Lihong,
Yes.
there is another question from Victor. So he's asking if one can deduce that it is better to consider L of trace class rather than a setup with von Neumann algebras of type 2-1.
I don't know. I think I don't know. Actually, I'm not expert, so I don't know whether it is better. But we only consider the trace class operator. So maybe it is interesting to see whether all this can be extended to this von Neumann type 2.
And then there is a comment by Conrad saying that the von Neumann type 2 case is certainly of interest, but then the present methods do not work.
Okay. I see.
So please go ahead. Thank you.
Okay. So let's look at the simple case. So when it is the X is finite dimensional, then actually it's easy, because when X is finite dimensional, then we will have always use this projection. So this projection satisfies that we can have the large enough n such that the dimension when k is large enough, when the n is larger than k, this xn, the projection of the xn will have the fixed dimension. Then we'll have, if it is finite, this only exists for the finite dimensional, when x is finite dimensional case. Then we will have this. So if rho n is belong to the t plus xn, so it's trace class positive semi-definite, then we will exist this the subsequence. It will converge in known one to the row, include its partial trace. So this is a very well known, this very good property when it is only correct when x is finite dimensional. Then with this, we can show this theory 1. It is just generalized for the finite dimensional case. Use this projection. So I will go quick. I think we don't have much time. But this is not true when you have this infinite, when x is infinite dimensional. So look at this simple example 3. Then we have this, we defined some rho n. This rho n converged in weak operator topology to 0, but rho n does not converge to 0 in the known one, and also its partial trace or not equal to 0 does not converge. So the previous one depends on the convergence of the known one of this density operator and its partial trace. So if it actually is infinite dimensional, it will not be true. Then we cannot prove. We cannot just generalize the finite dimensional case. So for when x is infinite dimensional case, so we have to introduce a new convex function. So it defines the partial trace and the known one. So for this it is a convex function, and we have this theory. So this optimization problem, the minimum goes to 0, then we have this lifting. So it is no longer a semidefinite problem. So to prove that, we have to prove this important lemma first. So suppose H1, H2 are infinite dimensional cubed space, and rho are a density operator in H1, H2, and the sequence goes to the converged weak operator topology to rho, and this we have the limit of this limit equal to 0. Then the limit of the rho n to the rho in the known one, the limit is also equal to 0. So in particular, this trace is also equal. So the limit of this rho n to minus rho in known one equal to 0 if and only if this trace also converge to the trace rho. The limit of this trace rho n equal to the trace rho. So this is a good property. So use this property, we can actually, so I skip this one. So we can use this property. Actually, we can show the sufficient condition. Method condition actually is easy. The sufficient condition is a little difficult. So here is just a sketch. So if this limit is equal to 0, we can see that the rho n converged in weak operator topology to the rho. Then we have satisfied this condition. So this is partial trace condition. And the second, we will need to show that the support of the law is included in X. This comes from also the condition of the weak operator topology. So based on this lemma 2, we can show that this is a sufficient condition. So 1 plus 2, these two conditions will see that law is a witness for the lifting. So at last, so we have also we will discuss, we defined this the continuity of the Hausdorff metric. So suppose we have this map phi from the trace class operate space th to the th1 sum the direct sum of the th2. So its map is the map low to the partial trace 2 low and trace 1 low, and it is bounded, and its image actually is just it can be defined by this set. So it's a low 1, low 2, low 1, low 2 are density operators in H1, H2, and also the trace are equal. And for each low 1, low 2 in this image of the phi, the mismap, we will define its pre-image by the M low 1, low 2 intersect with this kind of the positive semidefinite trace class operator. And we can show that this is also a non-empty convex compact matrix set with respect to the distance introduced by the known one on this space. We have the final theory. So this Hausdorff distance on the fibers over theta, a sigma, actually is a complete matrix. Moreover, the M low 1, M low 2, M in the Hausdorff distance convert to the M low 1, low 2 if and only if they converged in this the known 1 to the low 1 to the low 1 and low 2. So for the future direction, actually it is what we are discussing is about just the two spaces, the tensor product of the two space. You can think about for the n-part Cotton marginal problems, and for the well-known problem of the n-representation. And there are also other infinite dimensional optimization problems in the theory of quantum information, for example, discontinuous conjunction. So it is also about it was just recently proved by this G. It is not G and his colleagues, and it is not. We know that it is not true. So whether there is a counterexample, we don't know. And we know that in Sabine's talk, we know that for this proof also has some bugs or some gap. So they add some new result. And actually that one of the also the G, so he asked me about some problems about the duality infinite dimensional semi-definite program. So it will be used, it may be useful for them for some proofs. So we are currently working on these problems. So thanks.
Thank you very much, Lihong. So there were already some questions, but maybe we can take some additional ones. So if someone wants to ask for a question.
May I ask?
Yes, Bernard, of course.
A question. So, what do you consider here so for the duality in infinite dimensional semi-definite programming? So you have special functionals with convergence property?
Yes. So if and only if this X is finite dimensional, so we can prove that convergence. But if it is not finite dimensional, we cannot. So the difficulty is just this x. We should ask this some condition. So the x. So the lifting should be the support of the lifting should be included in this x. So if x is finite dimensional, then with this kind of semidefinite program, the limit will converge. Otherwise, it will not. So we worked on this problem. We thought it can converge, but then we find examples that it cannot. So we have to go to the non-one optimization problem for the infinite dimensional case.
Thank you.